For our last video in acid-base chemistry, we're going to be talking closely about two terms, neutralizations and titrations. Neutralization is the reaction that occurs between an acid and a base, because when an acid and a base are perfectly mixed together, they're no longer acidic or basic, they're neutralized. And the chemical laboratory process that allows us to mix those two things together is a process called a titration. Right, so let's first just talk about the generic acid-base reaction. An acid is anything that starts with hydrogen. So if we give ourselves HCl as an example, and a base is something that has hydroxide, this really is just a double replacement reaction. The hydrogen is going to replace the sodium and bond with the hydroxide, and the sodium is going to bond with the chlorine. So the first most common product of every acid-base reaction is hydrogen bonded with hydroxide, or H2O. The second thing is a term that we kind of loosely associate with any acid-base product. Here, sodium and chlorine, when it bonds together, yeah, that's the actual formula for the stuff that you sprinkle on your food. We call it table salt. But anytime we have any base reacting with any acid, the products are always water and then the salt of a chemical reaction. It's not always sodium chloride. It could be calcium hydroxide, and then that could have been calcium chloride as the salt. Okay, so because we know that when we mix together volumes of acid and volumes of base, they're going to neutralize each other, we can use a known acid or a known base to determine something about the other reactant. And that process is called a titration. Right? So from this neutralization reaction, we can calculate the concentration or molarity of an acid or a base. A titration uses a chemical indicator, like we've done so far in the lab, that allows us to say when the solution has reached a pH of exactly 7. So if we don't know something about an acid or a base, we can add in just enough base to neutralize the acid and say how many moles did that take, and then use the balanced equation to figure that out. Okay? So this setup is actually pretty similar to what we're going to see when we get ready to do our titrations labs here in a bit. All right, this long, tall piece of glassware is referred to as a burette. And it's kind of hard to see in this image, but a burette actually starts up here at 0, and for this one, it ends down here at 100, which seems kind of opposite to what you might think. Okay, there's a little liquid line. If this thing was completely filled up to the top, it doesn't tell you that it's 0 milliliters full. The purpose to a burette is that if you start at 0, and then you open this valve, which dispenses some of the chemical down below, if you start at 0 and you end at 60, you know the difference from where you ended to where you started is how much you dispensed. Okay? So let's say this volume here is at 10 milliliters, and then after a while, our liquid line is down here at 70 milliliters. What we want to do is take the final volume and subtract the initial volume. Okay, so that would mean 70 minus our initial volume of 10 means that 60 milliliters is dispensed. So that's why we always do final minus initial. So that's why our larger numbers are always at the bottom. You start small, you end large, and then the difference is the positive value that you dispensed through the burette. Okay? In the burette is always going to be a known molarity. That's like our standard. So we'll know the concentration and the molarity of what we put in there. And then in the flask down below, this is where our unknown is going to be present, along with our indicator. And after we titrate enough of either an acid or a base into our unknown, the change of the color of that indicator is going to tell us when we have to stop. Okay, so the process for a titration is actually a A lot of my students in the past have always said that it's kind of an enjoyable lab because it's in your control of when you need to start and when you need to stop. So it's kind of like a mechanical process. What we're going to do is take a measured volume of an acid solution of unknown molarity. So that measured volume is the key part. We're going to measure out how much acid we put into this flask. We just don't know what its molarity is. We're going to add 2 drops of our indicator, and the indicator that we're going to use is phenolphthalein. We're going to talk more about the image off to the right. And then measured volumes of a base of known concentration or known molarity are slowly added into the acid until the indicator barely changes color. So again, this we know the concentration of, this we don't know how strong it is, so we're going to measure and see how much base do we add in here until this solution changes color. Once the color changes just slightly, the endpoint has been reached. So in this image, these are the colors that we're going to see for phenolphthalein, for this chemical indicator. In picture B here, this is just a few drops of that base added in. You notice there's a little pink color, but the rest of the liquid around it is still clear. In picture C, this is the color of the endpoint that we want. It's called like a faint pink color, just barely there pink. One extra drop, and we have more hydroxide ions than we do neutral, and then it turns into this hot magenta pink color. This is the color we want to avoid. This is coming from just 1 to 2 extra drops, so we have to be very meticulous and very careful with how much base we add. Because if the goal was just to make the solution basic, we don't need to measure it out. We just pour base in until it turns pink. The goal is to figure out exactly how many drops of base are going to make that perfectly pink neutral color. Right? So what would these calculations look like if we collect all of this lab data? In the reaction above, we would need to predict the products, balance the reaction, and then using the volume obtained from the burette and the known concentration, we can use some stoichiometry to figure out what the unknown concentration is. So let's start just by figuring out the products of this reaction. We've got our acid here. This is sulfuric acid because that's the sulfate ion. And then this is sodium hydroxide. So the hydrogens are going to bond with the hydroxides. The first product that we're going to put is H2O. And then this +1 sodium ion is trying to bond with that -2 sulfate ion. So the second product is going to be Na2SO4 or sodium sulfate. Now, I think it's always easier because you kind of get lost in there's hydrogen there and only hydrogen here. I think it's easier to balance everything from the salt. You've got 2 sodiums here, so we need 2 sodiums going in. We've got 1 sulfate here, so we only need 1 sulfate going in. And if I put in 2 hydrogens and 2 hydroxides, then I'm going to make 2 times the amount of water. So there's your balanced equation. Right? So in the question here, we've got 25 milliliters of an unknown concentration of sulfuric acid, and that was poured into the flask, just like we're going to do in the lab. This unknown acid was titrated with a concentration of sodium hydroxide that's 0.2 molar. And then it says the initial volume of the burette was 12.5 milliliters, and the final volume of the burette was 37.5 milliliters. So in our burette, we started here at 12.5, and then somewhere down here we ended at 37.5. So really what we're calculating is what was that volume of liquid that's no longer present inside the burette. So the difference, 37.5 minus 12.5, winds up equaling a nice even 25 milliliters. Okay, so we used 25 milliliters of this 0.2 molar sodium hydroxide. What is the concentration X of this unknown acid? Well, one of the simplest things that we can do, because we have this 1 to 2 mole ratio, is we can use the volume and concentration of the sodium hydroxide to figure out how many moles were put into the reaction. So we're going to start by converting 25 milliliters into liters. And that concentration of 0.2 is saying that there's 0.2 moles for every 1 liter. Well, we can do 25 divided by 1,000 times 0.2, and we get 0.005 moles of our sodium hydroxide. Well, once we have moles of anything, we can use that balanced equation to convert. So 0.005 moles of sodium hydroxide for every 2 moles of NaOH. We need 1 mole of H2SO4. So 0.005 divided by 2 is equal to 0.0025 moles. And now we've got the number of moles and the volume that the H2SO4 had that number of moles in. So all we need to do is use the molarity equation. Remember, molarity is equal to moles divided by liters. So we've got 25 milliliters. We need to convert that to liters by dividing by 1,000. So the molarity of the H2SO4 is equal to 0.0025 moles divided by 25 divided by 1,000, or 0.025 liters, and that's equal to 0.0025 divided by 0.025, 0.1 molar H2SO4. So we had equal volumes of both, and this had to have been twice the concentration because we needed twice the number of moles. So it kind of makes sense that this was 0.1 and that one was 0.2 because we used the same volume of both solutions. Okay? So one more practice problem. We'll let you pause the video and try this out yourself. It says, what is the concentration of sodium hydroxide if 10 milliliters of 6 molar sulfuric acid reacts with 20 milliliters of sodium hydroxide? Go ahead, pause the video, try that out using the same reaction up above, and we'll see how you do. All right, just to make things easier, I'm going to rewrite the reaction down below. And I always like to fill in the information that we're provided. So we've got 10 milliliters of 6 molar H2SO4 and 20 milliliters of sodium hydroxide, but we're trying to find what is that concentration or molarity. Okay, so again, we've got enough information to figure out how many moles were put in, and then we can use that mole to mole ratio to figure out how many moles of sodium hydroxide were present in that 20 milliliters. Okay, so let's take a second to kind of break this down. We need twice as many sodium hydroxide or hydroxide ions because it's a 1-to-2 ratio. We've got twice the volume that we put in, and so our concentration should hopefully reflect out to see that if we have twice the volume and we had twice the need, that this should wind up being the same molarity. Okay, we'll see that in our numbers. But let's try this out. Okay, so if we've got 10 milliliters of our acid, we're going to convert that into liters and then use that molarity at 6 moles for every 1 liter. 10 divided by 1,000 times 6 is 0.06 moles of H2SO4. So if we start with 0.06 moles of H2SO4, for every 1 mole of H2SO4, we need 2 moles of NaOH. So then that times 2 is equal to 0.12 moles of NaOH. And that's the number of moles that was present in that 20 milliliters. So to find the molarity, we take 0.12 moles and divide that by 20 milliliters converted into liters, 0.02 liters, and that winds up equaling 6 molar NaOH. So again, just to reiterate that coefficient ratio, we need twice as much of this base than we do acid. So if we actually have twice the volume, there's the same number of moles dissolved, but we got double the number of moles because we doubled the volume. Here we wound up using the same volume, so it makes sense that our base has to be twice as concentrated or twice the number of moles dissolved than our acid.